Hello friends, in my previous video I have already discussed in detail about low pass filter, and in my this video I am going to discuss what will be the pulse response, different kinds of pulse response for a particular low pass filter, and I will show you the simulation also in the Simulink. Okay, so we'll visualize this same concept in Simulink. So let us discuss. So have a quick recap of our theory, whatever we have discussed in my previous video. That is, here this is our input we are providing in a series RC circuit, and we are taking output across the capacitor. Then this circuit will be nothing but low pass filter, and if you do the frequency domain analysis, the capacitor will be replaced by 1 by SC or 1 by j omega c, right? So that we can simply use voltage divider formula in this loop, and we can get the relationship between output and input, right? So V output by V input equal to this impedance by this impedance plus this impedance, right? So 1 by j omega c by R plus 1 by j omega c. If you simplify this particular term, you will get is equal to 1 by 1 plus j omega rc. J omega can be replaced by s, and we can get V output by V input equal to 1 by 1 plus src. Okay, this 1 by 1 plus src, now if you put R equal to 1, C equal to 1, what you will get? V output by V input equal to 1 by 1 plus S. So obviously that is also going to be a transfer function of low pass filter. And this particular block 1 by 1 plus S is directly available in Simulink in the continuous block. Okay, you can get that. So basically we can we can make such kind of block diagram representation for our simulation purpose. That is, as I have shown you, 1 by S plus 1, we are taking the transfer function of low pass filter by assuming R equal to 1 and C equal to 1, and here I am using one square wave signal generator. Okay, so basically that will generate our pulse, and we can measure the response using this scope. So I have two channel scope. One probe will basically see, one probe is connected to the signal generator, that is our input signal, and other probe is connected to the output of the low pass filter. All right, so now case 1, two cases I am going to discuss. So first consider the case 1. Before that, just keep this concept in mind. We have taken R equal to 1 and C equal to 1. This RC is equal to 1. So basically for this particular circuit, the time constant, as you know from the basic concept of your physics course or fundamentals of electrical circuit, already you have studied in your first semester, you know that the time constant for this particular circuit tau is equal to RC, right? So basically the time constant is equal to 1 in this particular case, because we have assumed R equal to 1 and C equal to 1. All right, now so now pulse time, and now case 1 we are assuming pulse time very greater than RC. Now what is pulse time of a square wave form? So see, if this is my y-axis, and suppose my square wave form, I am plotting one particular cycle. Suppose this is my particular square wave form which goes up to, suppose this. Okay, the particular time for which it is taking 5 volt or 1 volt is equal to that time for which it is taking 0 volt. Okay, so basically this particular whole time is called time period of the pulse. Okay, and the particular time for which the pulse is taking high amplitude or high voltage, that particular time range is called basically TP or pulse time. So in the initial case we have assumed pulse time very greater than RC. Okay, so pulse time means TP very greater than RC, or time constant for the RC network, which is acting like low pass filter for our this particular discussion. Now if TP very higher than RC, obviously we can say T will be very greater than RC, right? Because T is equal to, in this particular case for square waveform, T is equal to 2 TP, right? Because I told you the particular time for which the pulse is taking high amplitude is equal to particular time for the pulse is taking low amplitude or 0 volt, right? So basically 2 TP is equal to T, or time period of the pulse. So if TP or pulse time is very greater than RC, then obviously T is going to be very greater than RC. That means time period of the pulse is going to be very greater than RC. Now you just understand simply that time period is very greater than time constant. Let me denote it by tau. Okay, time constant for our this particular circuit. So if you take inverse, what you will get, frequency of the pulse is very lesser than 1 by tau, right? So basically we can say frequency of our this particular pulse is very lesser than 1 by RC, because tau is equal to 1 by RC, right? So basically this is what we got. Okay, so for this particular case one, when pulse time is very greater than RC, we can say frequency of our pulse is very lesser than 1 by RC. And for our this particular discussion, 1 by RC is what? 1 by RC is nothing but 1 by 1, right? Because RC we have taken as 1, so we have to take, for this particular simulation, we have to take frequency of our pulse of frequency of our square waveform very lesser than 1. Okay, so that's what I have written here. Pulse time higher than RC indicates pulse period higher than RC, so frequency will be very less compared to 1 by RC. So 1 by RC for our this particular discussion is equal to 1. So let us take frequency as 0.03 hertz, which will ensure this condition, that is our frequency of our square waveform is very lesser than 1 by RC, because 1 by RC is 1 and 0.03 is very lesser than 1, right? Now let us try to understand what will be our output waveform. Okay, so basically theoretically let us try to first understand intuitively what may be our possible waveform, and then we'll go to simulation, right? So basically this is our suppose this is our square waveform pulse. Okay, so from starting from this to this whole time zone is basically one time period, and this part for which the pulse is taking high amplitude or high voltage, that is basically TP or pulse time. Okay, now if our time constant is RC is what we are considering here, just see, pulse time is very greater than RC. Now if our time constant is that means what, our time constant is very lesser than pulse time. If our time constant is very less for our this particular circuit, what will happen, the capacitor will charge up very quickly and also it will discharge very quickly, right? Now you tell me, what is the capacitor charging graph? Capacitor charging graph, I am drawing roughly. Capacitor charging graph looks like this, and capacitor discharging graph, let me draw in this particular figure itself. Okay, capacitor discharging graph looks like this, right? So basically if for this particular circuit RC is very lesser than TP or pulse time, what will happen, the output voltage will charge up to VCC very quickly, so that very quick charge up, then after it will follow our this particular VCC voltage or higher voltage, and then it will rapidly discharge, because RC is very less compared to our TP, right? So basically it will discharge, and then again it will follow 0 volt, then again it will charge up very rapidly, and then again it will follow our VCC or high amplitude. That's what, let us draw step by step. So basically in the first instant the RC is very less because throughout the whole discussion our RC is very less compared to the pulse time, so that it will charge up very quickly, and then it will follow our this particular high voltage. So that here one black color I have denoted to indicate that our output is following our input, then it will discharge and follow the discharge curve of the capacitor. Okay, see, this is discharge curve, nothing but discharge curve, and then again it will follow the 0 volt. Okay, so that 0 volt, and then again it will go up. So like this waveform we should get. Now let us visualize this in Simulink. Let us check. So let me keep this. Okay, so let me go to Simulink. See, this same model I have implemented, 1 by s plus 1, nothing change I have given here, and this is our signal generator, square wave signal generator, and see here amplitude is 2 and frequency I have taken. So what is our discussion frequency? I told you 0.03, right? So 0.03, and don't forget to change the unit into hertz, because there are two unit available, rad per second and hertz. Let us take hertz because frequency unit is hertz. Okay, and click OK, and then press the run button and double click on the scope and see what kind of curve you are getting. See, this is our input pure square waveform pulse, and see our output quickly rising up, then it is following our input waveform, then it is quickly discharging, and then again following our input waveform. You can mark these two to visualize it more clearly. So if I merge, see, basically our this particular you can give legend also. So basically if I give legend, then you can see here it will show see the yellow color is square wave generator, that is our input signal, and the transfer function output is basically blue color waveform, which clearly satisfies whatever we have studied in theory. All right, so this is our first case one, that is when pulse time is very greater than RC. Now case two will be obviously reverse case, that is pulse time is very lesser than RC. If same kind of analysis you can do, if pulse time is very lesser than RC, that will indicate pulse period will be very lesser than RC. If pulse period is very lesser than RC, we can say in the reverse, if we take inversion, we will get frequency will be very higher than 1 by RC. So in our this particular case, we have to take frequency of our square wave signal very higher compared to 1 by RC. And as we have taken RC as 1, sorry for this, as we have taken RC as 1, so that what will happen, 1 by RC will be equal to 1. Okay, so let us take frequency is equal to 3 hertz. Okay, so the frequency is quite higher than 1 by RC. So and we will observe what may be the possible output waveform. So before that, theoretically, intuitively, let us try to understand. So this is our square waveform, which has higher frequency compared to our earlier case. Okay, so that less time period it has, and so that I have drawn accordingly. And now what will happen, see, our this for this particular case, what happens, that pulse time is very lesser than RC. Okay, so that pulse will go up, and after that it will go down very quickly. So as a result, our capacitor will unable to charge up to a to the VCC or maximum, that is this voltage up to VCC, and again it will discharge problem also will occur. So what will happen, see, basically I told you now that charging curve goes like this and discharging curve goes like this. So that charging curve, what will happen, the capacitor will start initially, it will start charging and charging, but it cannot charge up to the VCC. Suppose this voltage is VCC, in our this particular discussion it may be 1 volt or 5 volt, whatever, according to your adjustment in the signal generator. Okay, so basically a capacitor cannot charge up to VCC because our particular RC pulse time is very lesser than RC. So basically our capacitor will charge in this case slowly, and so that it cannot reach up to VCC. Before that our input will go to 0, and as soon as our input will go to 0, so capacitor will start discharging and it will decrease. Okay, so basically intuitively we can say that this kind of curve, in this particular case, when pulse time is very lesser than RC, we should use this kind of curve. Okay, so this is applicable when pulse time is very lesser than RC. Now for this particular implementation, we have taken frequency equal to 3 hertz. Let us verify that whether theory is matching with practical or not. So let me go to Simulink, and here let me change the frequency to 3 hertz. All right, click OK and just press the run button. And if you double click on the scope, see here you cannot exactly visualize this waveform because basically our input signal frequency is very high. And you can, let me go to view and layout, and let me split this, then you can understand. See, our input waveform is square in nature, but our output waveform is what kind of shape? This is basically a triangular waveform, because capacitor is just started charging, and as soon as the input goes to input again goes down. Okay, that is input goes to 0 volt, so that it will start discharging. Okay, so neither complete charging it can get, and neither proper exact discharging. Okay, so this kind of curve we are getting, and as it is obvious that from the theoretical discussion also we have seen that, see, the amplitude of our output waveform is far lesser than our input waveform, right? So here you can observe it here also. Here our amplitude is from -2 to 2, but here our this is amplitude for our input waveform, and this for our output waveform, it is restricted within we can say like 0.2 to -0.2 volt. Okay, so that basically it is highly attenuation is occurring in this particular case. Okay, so I hope you have understood this concept. Okay, this is what about pulse response for a particular low pass filter, which you should know, along with the theoretical explanation of the low pass filter. This is all for my this video. For the detailed explanation about the low pass filter, passive low pass filter, please check the description. I will post the link of my video which we have discussed previously. Thank you for watching.